So in the last video we looked at energy in general, but we didn't look at work in much detail. Work, as we know, is the way that energy is transformed, and it has a formula like this: work is force times distance. So if a particular force is applied in newtons over a particular distance, that gives us the amount of energy that is transformed. So if we were to make a graph of that with force here and the distance here, if we were to look at if it was a constant force applied over a particular distance that you're moving something, and then the area under the graph will give us the energy or the work done, same thing. So the energy used is the work done. It's not until we start incorporating time that we deal with power, but that's not the subject of this video. So just going to carry on from here with a slightly different way of looking at it. I want to use the example of a spring. Okay, we're not talking about a spring of water, we're talking about like a slinky, that sort of thing, a spring like that. If we consider, same thing again, a graph of force applied to stretch or compress a spring a particular distance. We'll call it x this time, just to distinguish it from the one above. What we notice here is that the further you push a spring, or you can think of a rubber band, if you're trying to stretch a rubber band, it's really easy at the start, but it's harder the further you pull it, or the further in a spring you compress it. It's most noticeable on large springs like car springs. If you try and push down to compress the spring, it requires greater and greater force to do so. So we'd represent that with a graph like this. It happens to be a linear relationship, it's very nice. And from this situation we can't use our formula because, why? Because the force is not constant. Not constant. If it was constant, then maybe we could, but it's changing. As you can see, it's increasing the further that you compress it. So what we would have to do, our rule still applies that the area under the graph gives us the work done, or the energy that has been transformed. So now we find that we have a slightly different formula for the work done or the energy stored in a spring. And let's just come across here to do this. And because it's a triangle, okay, it's a triangle. That's the section underneath the graph. It's got x across the bottom, and it's got f across here as that vertical height. And the area of a triangle is half base times the height. So in this case we're going to have half x times f. Okay, and that's going to give us the energy stored under here. There is a further step that we can take this, because if we just go back to our original graph here, this gives us a formula, f equals some constant times x. The constant is the gradient of the graph, and it works out as the spring constant, and the spring constant is a measure of how hard it is to compress or stretch a spring. So a spring with a greater spring constant will require more force and will have a steeper slope on this graph. A spring that is softer and easier to stretch or compress will have a shallower slope on this graph and have a lower spring constant. But this formula here, we can take this F equals kx and use it over here, substituting in for F, and that's going to give us another formula which makes things a little bit easier on us. Whoops, I wasn't meant to do that. We can take all of that information and put it into one single formula for the energy stored, which gives us one more different colour just to be nice. Potential energy in a spring is half kx squared, which is a very nice relationship. Looks like the kinetic energy equation, half mv squared, but it's just a consequence of area under the graph kind of thing. So that's just one way that we can use energy and look at it in a different way. Springs also come up in quite a lot of situations. When you're looking at the mass bouncing on a spring in simple harmonic motion, it's good to have this background as well.